when way back, 6 years ago, Soil CRC formed, we had those scoping projects to map out the landscape of what we were trying to do. So we were mapping out the landscape of the existing tools and models that were available with a focus on soils and trying to work out what was going on there. Then we moved on to, once we mapped them out, next phase of work was around improving some existing tools, building a better soil capacity into those tools. And one thing Richard mentioned earlier on today, that the soil is more complicated than the brain, and Matthew Evans said that soil science is harder than rocket science, because rocket science we can model stuff and scale it. Well, we're trying to scale soils, which is maybe crazy. The current investment at the moment is looking at how we diagnose complex soil constraints, and Suman, our PhD student, is working on that, and hopefully you've seen his poster out there. We'll touch on that a little bit here. And then Chloe, who is going to present the last couple of slides here, has just won this new project here around optimisation of soil constraint amelioration strategies or management. So there's a couple of completed activities. There's reports there. I think they're available on the Soil CRC website in the members area. If they're not, sing out, I can send them to you as long as you're a Soil CRC member. If not, we'll get permission for you to get access to them, hopefully. Okay, so the landscape that we were working in 6 years ago, a number of different tools available, some better than others. So some very heavily peer-reviewed, lots of science focus, some very simple ones, not so much. A range of different target audiences for those tools as well. So quite a complicated landscape to be working in. What I found quite useful out of this review is looking at how useful or easy to use some of these tools were in terms of their number of inputs and how intuitive they were to use. And there was a relationship between things not being intuitive to use and lots of inputs. And I'm openly admit I'm a bit biased towards AppTim because I use it all the time. It's got 50 different inputs. You know, probably it only takes me half an hour to set up a simulation, but those not familiar with it probably takes a couple of days. Lots of inputs makes it hard to use. That's a problem if you're trying to build decision support tools. So key learning from there was we need to make these things simple. How do we get that level of complexity that exists within soils and how we model them into simple to use tools where we can use alternative data streams and things like that, and looking at or existing databases so we can reduce the number of inputs. There's also, as part of that effort, we also started to look at the data landscape that was available as inputs into tools as well, and looked at lots of different data sources. This is just the soil-related data results up there, but we also looked at weather data and a range of other management data, financial data even as well. When we moved on to trying to improve existing tools, and we made some good efforts there. So there's a number of tools that we've developed and they're available. There's videos describing those developments and showing actually how to use them, available on the Soil CRC website now, and thank you to Olivia for getting them up. And those videos are actually lots of fun to put together. I'd highly recommend any project that's got some really cool outputs to think about creating some videos describing them. It was lots of fun, wasn't it? Yeah. It was good. Interesting. Never thought I'd do something like that. But just some of the key ones we worked on. So we implemented weeds into an existing tool called fallow arm. So fallow arm's a tool about fallow decision making. Not many decisions to make in fallow, but essentially how long you run that fallow for. We added some weed analysis into that, not the marijuana type, but the weeds we don't want, into there. And looked at termination dates of those weeds relative to when they started or when they germinated. So a weed essentially is a cover crop you don't want or you didn't plant. And if you use that tool, you'll basically find the similar themes of what just came out in the panel discussion there about these things take water in a lot of our environments. That's robbing water from the subsequent cash crop, and you don't get the, so you don't realise that immediate benefit from that cover crop, or in this case the weeds. Chloe did a lot of work around phosphorus and making phosphorus much easier to set up in AppSim. So APSIM has the capacity to do phosphorus. It's very complicated. I don't even understand it, but Chloe does. So she made it very simple to do, and there's a little app there now which helps me set up phosphorus and APSIM, which I think is fantastic. Another effort that Chloe did was rebuild the Gypsy tool, which is a sodicity amendment, a gypsum application amendment tool. Rebuilt it into in a new language, or into the R language, got it up as a web app, and added a lot of extra capacities, so some spatial analysis and variable rate application analyses into that tool, really enhanced its capacity. We've also did some work around accounting for nitrogen volatilisation in APSIM. So believe it or not, APSIM doesn't actually do nitrogen volatilisation, not yet, or not until now. We've got some basic functionality there now, which enables it to capture volatilisation losses through a couple of different methodologies. And also, Chloe did a lot of effort in trying to better represent water repellent soils in APSIM as well. So these then feed in through to existing decision support tools like CropArm, which is widely used in our region, in the Darling Downs and northern New South Wales for cropping decisions, and also into yield profit, because that APSIM is the engine behind those two tools. So our current effort at the moment, we've got a year left on this effort, is all about trying to diagnose multiple and complex soil constraints when they exist. So we're using a couple of different approaches, so using biophysical crop modelling to predict soil water properties, by feeding in crop management, climate information, crop yields. And so we actually have a methodology, I'll bring it up in a second, or the results of that, to actually predict what a plant available water holding capacity is without actually digging a hole to do it. And then from there, we're using some hybrid or some machine learning approaches to then diagnose and prioritise those soil constraints where they exist, and prioritise them for amelioration. Another part of this project is we're meeting with our grower group partners and getting a lot of information from them about what data is available that farmers can readily access to feed into decision support tools. So when we design these diagnostic approaches, we're doing it with that in mind, so we're not building an approach that requires a grower to go out and do an additional test. So as I said, we can predict plant available water holding capacity without a soil sample, without digging a hole now. This framework is computationally intensive. It requires a high performance computer to run, thanks to Francis, who's here, and his team from USQ research support for their assistance with getting this to work on our high performance computer. But what we do is we take crop management information, crop yields, the weather. We use the Salga soil grid as well as a starting point. We feed that into APSIM. We essentially run APSIM in reverse. Okay, that's the computationally difficult part of it, is getting it to run in reverse. And instead of getting a yield output, we ask APSIM what was the plant of our water holding capacity, that soil, to lead to that yield outcome. And we get pretty good results. So we can get an R-squared of 0.75 in terms of that prediction. And we've done that for a number of sites across Australia. I need to acknowledge here that we're using the National Paddock Survey dataset, which was collected by Birchip, GRDC and CSIRO through a national program there, and they've very kindly given us access to that dataset to run this analysis. Further on, and we're again using the MPS dataset at this point, this is again what Suman's been working on, and this is very early results, so he's still refining this model, but we're using some artificial intelligence process now to take existing soil properties that would be typically sampled through a soil test or a typical soil test, and using that to try to diagnose what soil constraints or what properties relate to soil constraints. So things like pH and exchangeable sodium percentage, and getting some pretty good relationships too there. So this is really exciting and very promising, because if we can start using those soil tests, basic soil test results, in combination with our predicted plant available water holding capacity and some crop yield information, we actually hopefully and will be able to say this is what the likely soil constraints are in that location. So now I'll hand over to Chloe with only like 30 seconds left.
Hi, thank you, Keith. I would like to talk about the next stage of what we are trying to do in Program 4 for the modeling activities. We are looking at how we can better optimize soil constraint management. And a key theme that has been echoed in all the talks today is about the complexity of soils. And soil constraint management is just as is taking the complexity to the next level, because soil, as we know, is this three-dimensional natural dynamic body, and it's very difficult to capture the intricate interactions between the different soil constraints at different plant growth stages and how that interacts to determine the yield outcome. And within Soil CRC, we were fortunate enough we can leverage what all the innovative solutions that we are trialing at our field trials. And that gives us a starting point of what those solutions can result in that space and time. And what we hope through these proposed new projects, hopefully will be contracted in the next few days, to use that field trials to then model it within agricultural system models such as Epsilon or maybe DSET, because the sugar model within DSET is actually the underlying model engine for the tools that sugar industry are currently using. So with that, by capturing that, we can then extrapolate our results in our field trials to different locations and time to reduce the uncertainty that's currently associated with the varied responsiveness of soils to the soil management practices we are trying to adjust for different soil constraints. However, most of these agricultural systems models does soil water and soil nitrogen dynamics fairly well. They don't capture a lot of the biogeochemical interactions of other soil constraints. So that's why we propose then using that extrapolation through scenario modeling of the field trials and extend it in space and time to generate a synthetic data set, and combine that with this vast information that we now have on soils, those spatial data sets, be it from digital soil mapping, radiometrics, and then use machine learning to better disentangle that mechanisms. And we propose it to do it in a way called knowledge-guided machine learning framework, where first is through parameter constraining. We select specific environmental covariates that we know are contributing to different soil constraints at different locations, and also we introduce it at different stages of an ensemble of machine learning algorithms so that it actually reflects our current understanding of soil science. And the hope is that then with the machine learning output, it can be more interpretable, that lead to actual practical solutions that farmers can use to better manage their soils for different places and agricultural systems. And the aim, I guess, through all the modeling work that we've been doing is that we want to assist to enable farmers to be able to make timely and spatially explicit decision making. And the model is only as good as the data that went into it. So quality data actually underpins our model development. That's why the field trials within Soil CRC are so critical in helping us to achieve that. And with our workshops, with our talk to farmers, we also understand that return on investment is really important to a demonstration of return on investment of adopting a soil management strategy and reducing the risk is really important. we are not going to do it in this project because this is more aiming to understand the mechanisms, but hopefully there'll be another project within Soil CRC where we can actually look at both the economic outcomes and the sustainability outcomes of these management approaches. And we also recognize this is also being echoed through the panel discussions in the morning. We are in such a data-rich industry, but the data collected in the industry varies largely. There's significant difficulty in harmonizing that data, standardizing that data to build an enabling environment so that data can be used effectively. So a part of this project, we will also look at, with the help of team members, Francis, who is a data expert, we'll look at how to help with the field trial data that gets into our modeling project. We will append metadata onto it. We will consolidate it to ensure its long-term usability and beyond the Soil CRC life, and to ensure it's fair data, so that other people can later on also make use of that. Thank you very much.